Hello, everyone. Today we are going to be presenting our presentation today with the title of Modern Control System Implementation on a Quadcopter. We have four members in our group, which consists of me, Kirana, Keira, Jesslyne, and Keren. So for the introduction, let's start with our main objective, which is to explore how LQR can improve the control performance of quadcopters, especially when compared to traditional methods like key ID. The system we focus on is a quadcopter, which has 6 degrees of freedom, 3 linear, and 3 rotation. And what is the reason that we choose LQR? Because traditional PID controllers are based on manual tuning and may struggle in high-dimensional systems like drones. LQR, on the other hand, provides a systematic approach based on mathematical optimization to get the best possible performance while managing energy use and stability. So let's compare traditional versus modern control. To understand why LQR is a strong candidate, let's compare them both. The PID controller is proportional, integral, and derivative terms. It's relatively easy to implement, but tuning the gains is mostly trial and error. This makes it inefficient for more complex systems like quadcopters. Whereas for the LQR controller, it is based on state space representation. It mathematically optimizes the control signal by minimizing a cost function. Instead of manually tweaking gains, we define what's important, like minimizing deviation or limiting energy usage, and LQR handles the rest. So what is LQR control? The definition of it is that it stands for linear quadratic regulator. It's an optimal controller that minimizes a quadratic cost function, which balances the system's state performance and control effort. The cost function is written as the equation that we have below. And the Q matrix penalizes deviation from the desired state. For example, position, angle, or speed. The R matrix penalizes excessive use of control input, like thrust or torque. By tuning these matrices, we get flexibility in balancing accuracy versus energy usage, which is ideal for aerial robots that have limited power.
Now let's take a look at the quadcopter state space model. First, we define the state factor. This model has 12 states, which include of orientation, which has roll, pitch, and yaw. The next one is position in the inertial frame, which is x, y, and z. The next one is angular velocities in the body frame, which is p, q, and r. And the last one is linear velocities in the body frame, which is u, v, and w. These states capture the full motion of the quadcopter in the compact mathematical form. The dynamics are written in state space form. It is shown here, which is the x dot equal to ax plus bu and y equal to cx plus du. These equations are linearized around the hover condition to get the A, B, C, and D matrix. The purpose of this model is to represent the quadcopter motion accurately, make the system suitable for linear control design. With this matrix, we can design an optimal controller like LQR, which will stabilize and control the quadcopter efficiently. Finally, we use the computed LQR gain matrix K in the control law U equal to minus Kx. For designing the LQR controller, there are 3 main steps. The first one is linearize the model. We linearize the non-linear quadcopter dynamics around hover. This gives us the A, B, C, and D matrix, either through symbolic math, simulation, or numerical methods. The next one, we choose the Q and R matrix. Q is the state weighting matrix. It penalizes deviation from the desired state. For example, if we care a lot about altitude or roll, we give those states larger values in Q. And the R is the input weighting matrix. It penalized actuator effort. Larger values in R mean we want smoother control and less energy usage. Step 3 is that we compute gain matrix K in Python. Using Python control library, we compute the optimal gain matrix using this line of code. KSE equal to control.OQR ABQR. This K will be used in our control law U equal to minus Kx. The goal here is to minimize the cost function J. This is the formula which blends state errors and control effort over time. In here, we have the implementation on linear versus nonlinear model. Let's first look at the linear model. We use idealized linearization quadcopter model. It's good for quick testing and understanding basic controller behavior. The control law U equal to minus Kx is applied using the A and B matrix. Now the non-linear model. We apply the same K gain from the linear model to the full nonlinear dynamics. This simulates a more realistic scenario where the system has real-world nonlinearities. The controller compensates for those deviations based on current state error. Looking at the graph, the linear model response is smooth and stable. The nonlinear model shows more oscillation due to the system complexity, but the LQR controller still managed to stabilize it over time.
On this slide, we compare two demo clips to show how simply tuning key and R changes the drone's behavior. On the left side, the performance-focused setup, which is large key and small r, drives the drone to follow the path aggressively. The blue, green, and red body axis vectors jump sharply, which means the motor slam on maximum torque to hit set points quickly. As a result, the maneuver complete in 2.4 seconds, but it demands high control effort and drains more energy. On the right side, the energy-focused setup, which has small key and large r, produces rounded turns and gentle axis movements. It takes 3.2 seconds, yet consumes far less power because the motors make smaller, gradual adjustments. With just a Q or R swap, we go from aggressive speed to smooth efficiency. No extra coding required. Now, let's take a look at the graph comparison from our simulation. On the left side is the high-performance controller. We can see that the X, Y, and Z positions drop very quickly. That means the drone reaches the target really fast, which is under 2 seconds. In the middle graphs, the roll and pitch have big spikes. These show that the motors are working really hard to make fast and sharp turns. On the right, we can see a big spike in thrust and power. So overall, the drone finishes the move fast, which is in 4.2 seconds, but uses a lot of energy, which is 36.9 units. So it's quick but not energy efficient. On the right side is the low energy cost controller. Here, the X, Y, and Z positions go down more slowly and smoothly. This means the drone takes more time but moves in a softer way. The roll and pitch moments are much smaller, which means it uses less effort from the motors. The power graph also shows smaller bumps, which means it saves energy. Therefore, this drone finishes in 6.2 seconds, but only uses 5.6 energy units. So, it's slower, but it saves a lot of power. This brings us to the main advantages of using LQR and drone control. The first one is systematic tuning. We express our goals in the Q and R matrices instead of manually tweaking 3 or 4 PID gains, and we see immediately how the trade-off shifts. The next one is MIMO capability. A quadcopter has 6 states: X, Y, Z, roll, pitch, yaw, and 4 rotors. LTR handles that multi-input, multi-output problem with a single gain matrix gate. The third one is explicit trade-off. We get a clear curve, So, if we want twice the speed, we'll pay in actuator effort. No mystery or unknown info. And the last but not least, which is fast retuning. If the UAV's weight or aerodynamics changes, just relinearize the model and solve again. No need for more trial runs. These features make LKR a powerful and reliable choice for modern UAV applications.
Next, we will start on the limitations and real-world challenges. The first challenge is linearity assumption. For the issue, the LQR is only valid near hover. Wheel quadcopter dynamics are nonlinear. How this may impact on the quadcopter, unstable or inaccurate during fast or aggressive maneuvers. The second challenge is no constraint handling. The issue is it invokes the actuator saturation and physical limits. The impact on the quadcopter, the output may exceed motor capabilities, which can lead to instability. The next challenge is full state feedback required. Some states like velocity or angles need estimation. Sensors can be noisy or delayed. How it can impact on the quadcopter, noisy or delayed state estimation affects the performance. Next is disturbance sensitivity. The issue is LQR lacks built-in disturbance rejection. The impact is just from the trajectory and delayed recovery from the wind. Next is model inaccuracies. Battery drain, payload changes, or wear alter system dynamics, which can impact the controller, become suboptimal or unstable. The final limitation is the implementation constraint, limited processing power sensor actuator delays in real-time systems. The impact is sluggish or oscillatory control due to the computation delays. Next, we're finally onto the conclusion. To conclude, the linear quadratic regulator has proven to be a simple yet effective strategy for stabilizing a nonlinear 6DOF quadcopter. Even though the controller is designed using a linearized version of the system, it performs robustly when tested on full nonlinear simulation. This shows its practical applicability. LQR uses a single feedback gain matrix to control all 6 stuffs, both position and orientation, with stable performance even in a nonlinear environment. We tested 2 configurations. The high-performance cost drone was able to accurately track the square path, but it consumed a total of 38 energy units, prioritizing performance over efficiency. The high-control cost drone, on the other hand, consumed only 12 energy units, but failed to perfectly follow the path. This setup prioritizes energy efficiency over path accuracy. This trade-off between performance and energy efficiency is easily tunable through the Q and R matrices in the LQR design. Finally, the entire design process requires no manual PID. Once the system is linearized, solving the Riccati equation directly gives us the gain matrix K, which we can immediately use to control the system. That is it for our presentation. Here are the references that we use. Thank you.